it comes to the communication, the protocols, and all that, I don't know very much about that, so I would not attempt to answer all the questions you might have. But basically, I think you can find information about the synchrophaser protocols from IEEE, or maybe should be freely available. And then the mean of communication, of course, it totally depends on what you have. It's sort of based on internet protocol. So if you have, in principle, if you have the IP address to the PMU, you could get the data. But of course, there are firewalls and so on to access it from the power companies. Okay, what do we use it for? First of all, this is the list that I still think is valid. First of all, it provides you with improved measurements. So that the ability of getting better measurements is a benefit in itself. Especially if you look at frequency measurements, the quality of frequency measurements is very good from PMUs compared to what once had before that. And of course, the ability to measure power angle in itself is an improvement. Then the next step in utilizing that information, it would be to improve, naturally would be to improve state estimation. And then it is so that you may recall that if from basic power flow analysis, that if you know the voltage magnitude and the voltage angle, then you compute the power flow. That's usually the solution to a power flow. That's the voltage, magnitude, and angle. So if you have good data for your lines and parameters, and you have full coverage of PMUs, you don't need to estimate the state any longer. You can just measure it. However, this opens up the possibility to also to improve data on your network. If you measure on both ends of a line, you can improve your values on the line parameters, for example, so we can estimate other things. So this gives you a source for developing new information system, I would say, to identify parameters in variables that you wouldn't be able to do before. After that the main emphasis has been to improve the power system security assessment, or the situational awareness in the system. That could be many things. It could be, for example, some power quality monitoring, measuring voltage flicker, for example. But we are mostly focusing on monitoring dynamic phenomena or stability properties, because that is what we could not do with without the laser measurement unit to the same extent. So voltage stability indices, angle stability indices, power oscillation monitoring, or identification of some dynamic system parameters. We'll show examples on all that. And also on control and protection. When we talk about protection, control first, We will come back to that, but there is a potential for improving the coordination of controls. For example, coordinating the control of fact devices, static var compensators in particular, for example, where that is used. In the Nordic power system, there is quite many static var compensator that is dynamically controlling voltage or reactive power. So optimizing the use of that is something that you could look into. And then there are examples of using PMUs for stability enhancement in terms of power system stabilizers or power oscillation dampers. And the idea there is that you could utilize the fact that you can measure voltage angle differences. And maybe sometimes that is a better signal than measuring the local power on a line, for example. You get the wide area perspective by comparing or measuring the variation in voltage angle, for example. And then it comes to protection. There are two areas that could be mentioned. It's not yet developed to much extent, but the potential is there, and that is for more sort of advanced or more reliable system protection schemes, making them adaptive to the system conditions, for example. When we talk about system, what I mean when I say system protection, that is various schemes for example, emergency load shedding. Generator tripping is used in some places in Norway. I'll also show that an example. So all these kinds of either emergency control scheme or special protection scheme to improve the utilization of the grid is a candidate. When it comes to more sort of specialized protection systems, what we have developed so far that I know of is a system for identification of fault or fault locations in networks with coil compensated grounding, for example. And that will also be given as an example later, how you can do that. I won't say more about it now, but there are some applications where the voltage angle or the angle information from PMUs can be utilized for protection. So situational awareness in the control room is one major motivation, and illustrated by this sort of high resolution detailed information that you could get. So talk about some application in short, and then we will come back to more details on those later on. What we have, one of the first applications that we developed and implemented at my university by one of my PhD students was an application related to voltage stability monitoring. And the idea here is that what you want to detect is the margin. You want to know something about the margin to where you would risk a voltage collapse, right? So I'll also come back to that later. Several applications was developed in this project that we had in the Nordic countries. This is something that were developed at the Royal Technical Institute in Stockholm, in Sweden, where we also sort of showed that you could have an app on your smartphone with all this information. From you could have your own state estimator on your mobile phone to keep following the operation of the power grid. So for the smartphone and for the iPad, we've made some information system to show frequencies and voltages. I'm not sure it's up and running, so I will see if I can demonstrate some of it tomorrow, but I'm not sure. Information of what you can, some sort of simple example of what you could, what kind of information you could get from the PMUs that you don't get from the SCADA system, sort of to motivate. That's what I have included here. This is a kind of large disturbance in the Nordic grid for many years ago, where we had some very early version of PMUs, just to illustrate the benefit. What happened in this case, if I remember correctly, was that there was a fault up in northern Sweden, and in this area there's quite a lot of hydropower plants, but there is not much people living there, so there's a surplus of power, and normally that is exported towards the south. This is where I live, by the way, Trondheim, or to Sweden. Then there was a fault up here, and this line was shut. And then you had an overload on these lines, and this area became an island. And what happened then is that all the power that was supplying the grid from this area was out. So you get a lot of power reserves activated here, flowing across this border, and overloaded those lines to a certain extent. Not overloaded, but at the risk of that. So first of all, it's not easy for the operator to see that you have had a islanding of the grid. But if you look at the voltage angle differences between the station up here and the station down here, you see that this is a very clear indication of a grid separation. There's no doubt that here there has been, so this can be detected in a fraction of a second actually, that you have an islanding. These are the voltage angle differences. Yeah. So clearly this part of the grid was separated from the rest of the system. And what happens then if there is a surplus of power here and a deficit of power in the rest of the system? That's interesting. This is a picture of what in, let's say, 5, 10, 20, 30, it's a half an hour, 50 minutes, as it's written there, of frequency measurements. So you see in the south or east, the frequency went down and came back, luckily. But in the north, you see the surplus area, frequency went high. And if you look at what information you get from the PMUs now, you can zoom in and look at the frequency. It was up to almost to 54 hertz before it came down. And you would have thought that that might result in a in a blackout or shutdown, but luckily the protection of the generator protection shut down some generation and it came back. And you see the frequency drop in the rest of the system, so it went smooth, but it was very close. And this is the information the operator didn't ever see. And if you look at the power flow on the corridor, which initially was very high, actually more or less above what they had allowed, it suddenly surged to more than 3,000 megawatt. And the transfer limit is 2,000, maybe it was 2,200, maybe it was 2,000. So this is a radical overload compared to what they allow. But they didn't know, so they didn't do anything. And it happened to go well. And you also see the power oscillations here, the electromechanical oscillations. You see 1, 2, 3, 4. Basically, it's the 0.5 hertz mode that is excited, I think. It's not totally easy to see. I think it's the 0.5 hertz mode. Okay, so what you could have done is to apply some system protection scheme, right? And what is normally done in this area, see if I have a slide on that. Is to look at the system protection. I can give you an example. We can come back to it later also, but I can illustrate just that one. Again, we're looking at that corridor here, where you have sort of a limit about 2,000 megawatt. But that is actually above what you could get, sort of, if you want to enforce the N-1 criterion. You could probably only support 1,500 megawatt on this corridor. So what is done is that you have what they call a system protection scheme, where you have generators here. You have generators here, of course. And if you have a sudden outage of one of these lines, then you send a signal to trip this generator. And what happens then? Well, the other generators will provide primary reserves, so will the ones in Sweden. And the effect is that you have reduced the power transfer. So the system protection scheme does immediately reduce the power transfer to avoid overload in such a case. But this is not 100% reliable. And that is that you have two examples of that's not reliable, because actually at 3,000 megawatt, the system protection should have tripped, which would have made a loss of another maybe up to 1,000 megawatt, and then you would have really trouble, really have been in trouble. So it was a luck that the system protection in that at that moment did not work. But there is another example that it actually tripped when it should not do. And that is seen here. There was a short circuit down here, which affected the relays on that line, so that it initiated a generator trip in the western side of Norway. And that is also critical, because then you had a loss of generation and you had actually quite some oscillations in frequency. And also you see that the power flow on the line was reduced, but the damping was good in this case. The electromechanical oscillations was well damped. But it illustrates the fact that you may have unwanted operation. You may not have operation when you need it. So the dependability and security of such protection system is important. So a challenge to you is sort of how can you make more reliable and precise system protection scheme by utilizing the information that you have from PMUs. Okay, that was we will come back to all this. A little more on the voltage stability, power oscillation, and applications. If we look at voltage stability assessment, what you have today, if you are lucky as a system operator, you have some tools in your EMS system that is able to do some power flow calculation to estimate some limits due to voltage stability. That is good, but in an online setting you need to get fast information. If system changes suddenly, the SCADA EMS system is not able to update probably, so a useful addition to the EMS system would be to have some indicators based on PMUs in an online setting. So an objective in this, I think, perhaps put this here so we not have so much echo. Our objectives have been to develop robust and simple voltage stability assessment tools for online application. And that we think we could do by combining PMU information with possibly with information from the state estimator. And the idea for many of those of these applications that have been developed, and which you will see in the literature if you do a literature review on online voltage stability assessment, is that the idea is that you on one hand measure the load by having a PMU that can measure voltage and current, compute the sort of the load admittance or load impedance. And if you then could estimate the strength of your network, or sort of estimate the what you could call a Thevenin impedance to represent the strength of your network, then you could track sort of when you approach the maximum power transfer. Because if the load impedance then approaches the value, the magnitude of the network impedance, then you are in trouble, because then you know that you are on the maximum transfer side. You are on the point of the nose curve here. So that is a sort of a simple and understandable indicator, but it's not that easy as it looks to estimate this impedance of the network, and it may not either be the best indicator for voltage stability, because it's too simple in some way. But the principle is nice, and then of course what you need in an online setting is to have some idea of not only when you have your maximum power transfer in normal operation, but what would it be if you have a contingency? Would your maximum transfer be here or here or here or here? So in order to give you a basis for setting a margin or setting the limit. So that is something we have looked into, or not, different people. And this is one of the applications that we are still running. It has been in operation for more than 3 years now, actually, with input from Statnett, but we are deploying it at different locations to get more experiences with it. And you see, this is what this is able to do. May not be easy to see, but up here you have a trend curve of the load impedance. Down here is the estimated network impedance, Thevenin impedance. So we see there is a good margin here at the moment. And this is the actual power transfer, 1800 megawatt in this case. This is the estimated maximum transfer. So this is the margin. And together with the trend curve, we have a live curve of what we estimate as this voltage versus power curve, the nose curve. So we see that we are the point, the dot here illustrates the operating point with the voltage and the transfer. And this is the estimated sort of maximum transfer. And you see there are some curves to help you here. And this says, for example, that okay, if the network impedance was exactly 30 ohms, you would follow this curve. And it's nearly 40 to 30 ohms now, so we are close to that one. But if for some reason we had an outage so that the network impedance rise to 40 ohms, this is 40 ohms, then we would follow the green curve. So if you knew that there could be an outage resulting in 40 ohms, this is your margin. And this is the indicator that we have developed that I will explain later on. But this is based on an online sensitivity calculation. And it's perhaps not intuitive, but when you're used to it, it's actually very good information, because basically it says that if you are on the slope here, you are safe. If you are at the bottom, then you start to approach the margin, and if you're out at on the upward trend here, then you're in sort of trouble. But you don't lose stability until you go above the red line. But we'll come back to that. But this is an application implemented in LabVIEW software, National Instruments LabVIEW, and run on my computer that is connected to the transmission system operator. That's one example. Here you can see sort of when things change a little bit. In this case, the network is weakened a little bit, so you move from up to another curve here, and your margin is reduced. But so far we didn't, you might say luckily or regrettably, we haven't had a voltage collapse, so we couldn't test it fully tested. But I hope that there will be a small collapse someday so we can really test it. Yeah?
How about this, after the collapse point, how do you get this point of the router? Where person of the network? Because after the bifurcation point, and after the collapse is obtained.
Oh, after the collapse, you don't do it.
Actually a collapse.
No, I mean, and this is the concept. I try to be precise on that. I'm not talking about the stability point. I'm talking about the maximum power transfer, because you don't know from this whether this is a bifurcation point that results in instability, but you know that it's a maximum transfer, and it's likely that you will have a voltage collapse or a voltage instability phenomena when you reach that point.
Any condition that we were to try to solve by continuous loss, and then you would
Yeah, that's the other idea. That maybe I have a slide on that later on, but the concept, what I try to develop is something that is a combination. And I have a master thesis on that that I can send to you. Yeah. My idea is that the system operator should run contingent or continuation power flow up here, which updates itself as fast as possible, of course, with the information it gets, but it's not real time. And then in parallel to that, you have this indicator that runs online, and then you could use you could calibrate the two results in a way to get better information. Exactly how you will calibrate it, that could be discussed, but we have just started to look into that. But there are two different approaches. One is purely based on the state estimator and contingency power flow, and this is purely based on measurement. But you could do a mix. You could have a partly model-based approach to this as well. Yeah. Yeah. For example. Yeah. So that there is one paper or two papers also by me and my student took that combines the approaches, that makes a small observable part of the grid and uses that together with the model-based indicator for the unobservable parts, just put it like that. But experiences so far is that this application is working fairly well. But of course we haven't done the real-time testing for the actual collapse other than in laboratory conditions. But I have some. I have a slideshow showing how it works in the laboratory. Okay, we try to come back to all this. Next is these nice colors. Yeah, yeah, but it works. You see it there. It's just to highlight that. Yeah. I'll talk a little bit about power oscillation monitoring. just very as an introduction, because we'll spend more time on that. The motivation, it's better to look at this one. One motivation for looking into power oscillation monitoring is in the Nordic system. And of course there are many similar objectives other places. But we have in the far north of Norway and Finland, way above the polar circle, where it's the sun never shines at this time of year, we have a weak network. There is a weak link here through northern Norway down in Finland. And there are PMUs all the way around here. And this and the limit of export or import between Norway and Sweden in this area is limited purely by oscillatory stability or angle stability, actually. So here there is a clear need for monitoring of those oscillations to be aware of where to set the limits and when you need to do something. So the approach by our Finnish colleagues is to try and monitor frequency and damping of the power oscillations based on ambient data. That means the normal oscillations. That is inherent all the time, but hopefully sort of sufficiently damped. And the colleagues, Janne Seppinen and Jukka Turunen, which are the two persons who have made most publications in this area, have looked into several methods. They have made their PhDs on that subject and have sort of found quite reliable methods to monitor the damping of this mode in real time. You see that it varies here from 10% down to 5% over some hours. And of course, what one wants to do with that is to implement it in other places. Now this one is better suddenly. So the application here was up here in the far north. And, but there are other interesting applications in the south, in the Hasle corridor, for example, between Sweden and Finland, where you have the 0.3 Hertz mode that limits power export from Finland to Sweden, also by angle stability. So there are several places where this is needed. I'll come back to more on the different applications later on. Another area of interest is in utilizing the measurements to identify certain properties, dynamic properties of the network. And that is, it's useful for several purposes. For the analyst, it helps in improving the model, validating the model, getting better parameters. For the operators, he wants to know exactly how the performance of the generator is. So one of the applications we have been working on is online, sort of in an online setting, to estimate certain properties. And one example here is the estimation of what we refer to as frequency containment reserves. In other words, we want to estimate things like the speed group of generators, the what we call it, the rho parameters yesterday, because that is a measure of the provision of reserves from that generator. You can turn that into the megawatt per hertz. You can measure directly the megawatt per hertz. But in addition to that, what is the, I mean, the steady state is one thing, but what is the bandwidth? Is that right? Bandwidth, maybe it's written differently. But these are the questions that is interesting for the operator to know. Do the generator provide the controls that they are contracted to do? Do they do what they are paid for? Now we can go to this place. And the starting point here is that frequency is seen to vary maybe more than before in the Nordic system. Also in other power systems, the trend is the frequency is varying more than before. And it's not easy to see, but I can show you. No, I need my glasses. .49. Yeah. The operating range in this case is from 49.9 up to 50.1. This is the allowable range of frequency. But we see that the variations, the normal variations, are sort of covering the entire band. So we would know that for any sort of disturbance we will get outside. And this is seen in this picture where they have counted, the transmission system operator have counted the number of hours, or minutes in this case, minutes per week, that the frequency have been outside. And it is increasing. Might be due to better measurements, but I think there has been an increase in the frequency variation, and that can be explained by many reasons. More wind power or variable generation is one cause for that. Maybe some of the governors are not well tuned in the hydropower system. Maybe the generator owners does not pay attention to that because they don't get paid for it, as they think. I mean, enough. They want more money, of course. So it is important for the operator to know the performance of the power plants. So the droop setting, if they can verify the droop setting in online, that would be nice. But it's steady state is one thing. The system, power system is never in steady state, as you see from this picture. It's always moving, sort of. So we would also like to know what is the bandwidth. Does it perform at higher frequencies? So what one can do, what I did in the Nordic, the TSOs in the Nordic power system, is that they went out to measure a lot of things, and they could measure the transfer function on generators from frequency input to active power and they could see that this is the magnitude and this is the phase angle. You can see that the bandwidth is if you say that okay, the bandwidth is 2, 3, 4, 5 is half the magnitude at steady state. This is an indication of the bandwidth. From the slowest generator to the fastest one, it's a very big difference actually. And the same goes for the phase angle, the phase shift. But you see that the performance is very different. So what is the truth? Well, it's at least we have found that it's possible when you have variations in frequency to estimate fairly well that the turbine governor parameters in an online setting. This is based on the fact that you measure current and you measure voltage at the point of connection of the generator, and then you compute electrical power and the frequency and put that into a system identification algorithm, and the output is then what we hope is correspond to the transfer function of the actual governor and turbine. So, I mean, this is just an illustration where you have consider the governor as being a hydro turbine governor, hydro turbine and governor. That is the classical one that I showed yesterday. And then when you have a sort of a window of measurements, in this case, the frequency measurement in blue from 49.9 to 50.1 hertz. So you have variation within the allowable band, and power output in another scale here, of course. But you see, here the big trend is what you would expect, that when the frequency go down, the power goes up, following the droop characteristic. But what is the performance of that? That is what we are after, and what we can estimate then is the transfer function from frequency input to power output of the turbine and governor. And you see that you can measure what comes out of the identification algorithm is this green curve. It's keeping the sort of constant gain up here until you are at sort of reach the bandwidth of this system. And of course it drops off at a certain point, so you have in a way verified these measurements that the manufacturer themselves can do. And how good is that? To verify it, one could do several things. What we did is to put the frequency measurements as input to a model that was validated through this green curve, and compare that with the measured ones. And then we took the frequency measurement from the measured data and put them through the standard HIGO model with its standard default parameters that you get out of the textbook. And then by putting the standard parameters in, you get the red curve. And using the actual validated model, you got the green curve, which you see correspond then very well to the measured ones. While the theoretical one is slower. And that is also seen here as the frequency response of the model curve is lower. So this confirm that the generator in question here has a very good turbine governor system. It's faster than sort of the default model parameters indicate. And that is, I believe that is correct because I have been there and I've seen that this is a well-performing generator. So that is an example, and we'll talk a little bit more about this work also later on. You could also, I mean, there are much to say about this. You could test it during a transient. It also works fairly well during a transient. Essentially, you get the same information. Should we take a short break before we take the rest now, maybe? We kept on an hour again. I think we do that. 10 minutes, is that enough? And of course, if there are questions, we take it now. Yeah.